the exact number. But I have no idea where they're sourcing these lasers from. I don't know anything how they built the device, so I'm sure we can get that information. We'd have to follow up separately on that, but I don't know those details at all.
All right, thanks.
Yeah.
Any other questions? Yes.
Rich, just to clarify, the SerDes on this latest quantum switch, is it 200 gig SerDes?
Yeah.
So how does it connect to ConnectX 8, which is 100 gig per lane, as far as I understand?
ConnectX 8 is 200.
It is 200?
Yeah.
So
it's also XDR.
Hmm?
It's also XDR signaling. They're both 200, that's 200 gigabits, 200 gigabits per lane on both sides.
So in Ethernet mode, it's 100 gig? And
Ethernet mode today is 100 gig, that's right.
InfiniBand is 200?
Yes. Yeah.
Hey, Rich. So I get all the advantages of silicon photonics versus our traditional optical with external transceiver, right? But what is the comparison to, and what happens to copper in this world, right? So we still mostly use copper in rack, right? And then just switch to switch links or optical for cost.
That's right. So this is only a switch to switch technology. It's not, we don't support the co-packaged optics with the device. And copper is one of the reasons we don't.
Okay.
We don't want to lose we don't want to lose the advantage of copper as long as we can maintain it, right?
So like, would the top of rack switch be a mix of optical and copper in this world, or because if it's a switch to switch technology,
No,
at some point you have to do a switch to card, right?
Yeah, but that's done. But I don't know. I could guess, but I don't. It would have to be, otherwise it wouldn't work, right? Because there is no support for this in the HCA. I asked about that too, if there were plans, and there no.
Any other questions from here or online? Are there any questions? Okay, so let's give thanks to Ray. So we'll move to the next talk. It will be presented by Srijeet from Enfabrica. So just to introduce him, co-founder and chief development officer, where it comprehensively defines and drives the architecture, engineering, and innovation pipeline across software, hardware, and systems. Prior to founding Enfabrica, he was an architect in Google's network infrastructure group. Previously, he was VP engineering at Cumulus Building Software to revolutionize open networking. At Cisco UCS, he was director of the architecture and software working on the NIC and virtualization systems, later known as DPUs. At SGI, he was part of the advanced graphics team that invented floating point frame buffers and programmable shaders that underpin today's GPUs and accelerators. So Srijeet is on the Linux NetDev Society Board of Directors, and he has 64 issued patents. He holds an MS in the computer science from the University of Oregon. And yesterday, Enfabrica gave a tutorial, but today we will be talking into more Enfabrica accelerated compute fabric, architecture and use cases. And as we saw also, they have a demonstration here. And yesterday, many of you have talked to them. If you have not talked, please feel free to talk to them. So let's give a big welcome to Srijeet.
Thank you, Dr. Panda. I learned things about myself I didn't know, so that was useful. Okay, looks like we are ready to go. So I see. This is not going to run in split screen. It's going to go just main screen. Is that okay? Okay. Thank you for having me here. This is my first time here, and hopefully I'll get a repeat invite. We'll see how that goes. So I'm going to talk about the ACF, which is our first chip, the ACFS, as Boris correctly said yesterday. And I'm going to give you a little bit of, the talk is a little different from, I think, the talks we've done in the past. I've tried to sort of show the power of the chip and hopefully engage much of the audience and see if, actually, I think we should be okay. And see if I can get some more participation and some ideas engendered and get some of those students that Dr. Panda talked about to engage with us and do things in a slightly different way. So, yeah, okay, it's on. So to start, right? So this is the chip, right? You've seen the box, you've heard a little bit about what it can do, but this is the box. So if you look at the box, yeah, that's not what I wanted to do. Yeah, it's fine. I'll just use that. Yeah, that's better. Okay. So if you look at the chip itself, right? The first sort of the overview of the chip is a lot of lanes on the Ethernet side, a lot of lanes on the PCI CXL side, designated as green and blue in this picture. And it's got think of it as two crossover planes. One is an Ethernet crossover plane shown here, and one is a PCI CXL switch type fabric shown here. We call them the two crossbars in our system. And in the middle is what you could think of as a whole series of NICs, but in reality, we think of them as copy engines. It's got a memory translation capability. It has pretty significant buffering, Tor class buffering, almost 100 megabytes. And it has a fairly sophisticated control plane that allows you to do a bunch of things. So in terms of absolute speeds and feeds, on this side, this is 32 lanes of 100 gig SerDes, so it's a 3.2 terabit network device. And on this side, it's 160 lanes of Gen 5 by 16 currently, and in a subsequent device, we will be moving that to Gen 6. What else do we need to talk about? The copy engines, the things that sort of power the device. Think of the copy engine as something that can move any byte from any of the green links to the blue links or vice versa. In fact, it can also do it between the green links and between the blue links itself. So it's effectively a full byte accurate crossbar that can take bytes from any direction to any other direction. And why is this interesting? What this allows us to do, right? We heard a lot, and you will continue to hear a lot, of architectures that talk about taking one of these links and making it faster. A lot of effort in the last few years has gone into congestion control, better networking protocols, things that will make any one of the links become more efficient. But we assert that that's not sufficient. In fact, there are simpler, more elegant ways to solve this problem, which is effectively give you path diversity and protocol interoperability. So what is unique about this picture, and if you have spent enough time looking at what system architectures look like, some of which Dan talked about this morning, the internal design of those systems are what I call a stovepipe design. You typically put a processor, a NIC, and a switch port in a line and say, the only way to get faster is to make that stovepipe faster. And that basically leads to two significant problems. The first problem being, you can only get faster when every component in your stovepipe gets faster. Otherwise, you're stuck at the speed of the slowest component. And the second thing is, it means the only way you can get more efficiency is by driving efficiency close to 100%, which in the modern world is going to be a constant struggle between small messages and large messages, because overheads and routing will become a factor. Our design instead says, what if you had a chip, and it's no longer a theoretical, the chip is there, you can see it working. What if you had a chip in which you could say, I can interoperate any speed, any link with any protocol? And structurally, what that means in this picture is, you could come in, and we'll talk about this, at 800 gigs on an Ethernet port and deliver that bandwidth to multiple PCI ports on its own. You could build logical circuits that connect one PCI port across an Ethernet link to somebody else and effectively manage and maintain its efficiency and treat it as a logical circuit by using the path diversity that was available to you. This is what we set out to do. And what I'm going to do in the next few slides is, and the time available to me, which I'm sure I will overrun, show you a few ways in which it can be used. So we're going to first talk about how a device like this effectively gives you elastic bandwidth, a bandwidth model that is not going to limit you in any interesting way. So first, let's look at this chip on the inside. The way the chip works and the sort of the internal architecture works is there's effectively, like I said earlier, two crossover points. And for the purpose of this discussion and today's conversation, consider this as your Ethernet crossover plane and consider this as your PCI CXL crossover plane. The interesting thing in this picture that you should note is that any packet coming in on any Ethernet port can be directed into these things that we call virtual queues. If you're familiar with switching, which I see a lot of people in this room are, virtual output queues are a well understood concept. You can think of this as a virtual output queue. So if you think about this as a virtual output queue that I can drive any packet into, what this allows me to do is to say, when a packet arrives at a port, I can construct its metadata and put it in this virtual output queue, while the payload on a parallel interface goes into buffers. This virtual output queue, which you can think of as roughly mapping to a flow, can then be dequeued into any location on the other crossbar. But note that the data plane, shown here in blue, is completely orthogonal and completely parallel, which means in this example, if these 3 ports were 800 gig, I would get 2.4 terabits of metadata here, but 2.4 terabits of payload here, and I can dequeue, well, in this case, it's PCI, so you can only dequeue at 400 times 3, so 1.2 terabits, but completely in parallel. There is no bottleneck in the system from a data movement perspective. And the same scheme is available to you when you're going in the opposite direction. I can pull from every one of my PCI ports in parallel and serialize them out to the network, and I can serialize them out using ganging on this direction as well, as we shall subsequently see. By the way, feel free to, if you have a question, feel free to interrupt. I'll try to adjust time. If you want to hold your questions, thank you. And we'll come back to it. From a software perspective, what does this mean? And that's, I think, one of the best things about this solution. From a pure software perspective, this presentation of buffers is just an SGE or an array of SGEs. If you're familiar with RDMA concepts, it's basically a scatter-gather list. The only difference is that our scatter-gather list can now span devices, hosts, complete PCI domains. The elements don't have any knowledge of each other. The scatter-gather list head is the only thing that knows about where everybody else exists. And the entity that's managing this list head doesn't have access to the actual buffers either. Doesn't even need to know where they live. So you could basically have a single entity connected to us say, put the memory in those guys as memory, or put the data in those guys as memory, and I don't even know where those guys live. It's completely orthogonal. Similarly, on the network side, the way the network is represented to software is it's basically ports or path in a queue pairs or in a RDMA connections communication channel. So if you have a channel or a queue pair, whatever path it was going to take, whether it was going to reach the other side as some address identifier, or it was going to reach the other side as an IP address, whatever that scheme is, the network ports will support it either as a single port or as a gang of ports if you're doing any kind of spraying or distribution type algorithms. So the simple statement there is the software representation of this fits into your current programming model already. There is not a single concept that the software model enforces that requires you to have to rethink how your apps will work. So let's again examine a little bit more about what that means in practice. So one of the things that Boris talked about yesterday, right, was this thing we call emphasis, which is our memory box. The problem that the memory box solves today is that these PCI ports, or CXL ports, are actually in today's product offerings not that fast. That is one of its biggest issues. CXL, like if you actually looked at what Dr. Panda presented as well, the bandwidth and performance out of CXL isn't that great. And putting it into the load store path actually creates more complications and complexities. So what we say is don't do that. Put memory attached to us. We will take bandwidth off the network in multiples of 800 gig, and we will allow you to stripe them into multiple CXL devices such that you're effectively ganging the capacity of the CXL devices from a bandwidth perspective. Now, we can do this at 800 into 2 times 400, or we can do it at 3.2 into 8 times whatever CXL bandwidth that you can get. Because the bandwidth striping or the capacity available from striping scales linearly. And I'll show you some data to that effect at the end of this talk. Another way in which networking bandwidth elasticity can help you is a problem that happens in almost every machine learning type application and HPC applications is incast, right? Tons of scientific papers, research is going into how to handle incast. One of the things we can do is don't have incast, right? So in a design like this, what we can effectively allow you to do is, as I said earlier, all your bandwidth comes into this virtual port. But since this payload is delivered completely in parallel, if you had a compute complex where the memory bus allowed you to say, I can access that memory from multiple ports. Now, I've shown this as a GPU mesh with a private bus on its inside, but this could just be an x86 processor with multiple root ports. All you need really is a uniform memory access module or model on the right-hand side of the picture, and we can deliver the bandwidth in parallel while keeping the control plane serialized, which means what you see is effectively a 3.2 terabit flow while all the bandwidth is arriving in parallel. So you've gotten all the benefits of a flow, but you don't have incast. Yeah. I'll show you some data. Hold that question to the end. We can address it when we get there. So as I said earlier, right, so the GPUs are attached here, and on the network, we are doing generous receive, which means you can actually use all your network distribution, DLB, what did we call it, adaptive routing, pick your favorite industry term, to make sure that the packets are also completely sprayed on the network side, so you can use the fact that you have parallel network paths to your advantage. Another use case, another two use cases, this is what I was alluding to yesterday, for people who are trying to do collectives. And specifically, I think this is for this conference, the thing I'm hoping we'll get some people excited and willing to participate with us on. So if you think about the problem of a broadcast or an all gather, right? The classic way people are doing it today looks a bit like this. You come in on some network port into one accelerator, and then you switch it to the accelerator's backend bus and say, hey, that thing is running at 900 or 450 gigabytes per second. It's 10x or 100x faster than my front-end interface, so I will just do my broadcast on the back end. True, you can do that. But it has a cost, right? In that case, the front-end processors, the SMs, as NVIDIA calls them, are involved. You're actually taking time away from compute to make this happen. What we could do instead is we can say, come in and distribute it directly. Our chip is capable of doing wire speed replication. So what you will get is effectively a broadcast or a multicast effect coming straight out of the wire. And you did not need to engage your front-end processors at all to make this happen. Okay? So the benefit here now is that a single packet payload can be replicated, and more importantly, because remember, these guys are represented as a scatter-gather list, I can actually even move them into specific locations. So there is no requirement that these buffers on these three ports have to be at the same address. I can move them to whatever location I want. Another way in which such a mechanism helps is an all-to-all type collective, right? Where you're trying to do, the classic answer again is, I'm trying to move a piece of that red buffer to different locations. Your best case, you may have multicast support in your switch, and you can do that in a single shot. That still means if what I was trying to do was an all-to-all, I'm going to do this for red, then I'm going to do it for blue, then I'm going to do it for green, then I'm going to do it for yellow. Your even better case is that you have perfect scheduling and like ultimate management of dead time between the different collective operations. But if you instead had us, you can do this. Because what you get to do now is you get to specify a scatter list of source and a gather list of dest. And you would enqueue them into our control plane, and it would do as hard as possible work-conserving scheduling. It'll stack them all up and execute them back to back, such that the bandwidth on every one of your input ports and your output ports are maximized. And as far as the host or the GPU or the SMs are concerned, this is free. You do nothing. Okay? And remember, and this is the important part, this part or this model of communication, this communication strategy is available in a factory or a class type architecture. So everything that we are talking about, and if you remember the conversation we had yesterday with, I'm not seeing the guys I was asking this question off of. If you think about communication as a pure networking problem, and you say that it does not address the part that is on the NVLink or the UA-Link or the HDMI buses, then you end up with two different primitives and parameters in which you can move these data sets around. In our scheme, we actually don't have that problem. Whether you're doing this on the inside, which is what I call the communication path this way, or you're doing it on the outside, which is you go out to the wire and then you do the same thing on the other side, the primitives remain the same because all you're effectively doing is saying, I have a scatter list and a gather list. And from the scatter, I'm going to serialize, and then I'm going to deserialize into the gather. Whether that serialization to deserialization happens across an Ethernet wire, or it happens within our fabric into PCI CXL, the application and the endpoint usage model does not care at all. As I said before, if any of what I'm saying doesn't make sense or sounds confusing, stop me and we can, yeah. Yeah, there you go.
Do you have access to the communicators, which outgoing switches or ports are the part of, and then
Great
trying
question.
to multicast on that?
Great
Slide
question.
9.
Great question. So the question was, do we have access to the communicator? You're talking about the CCL communicator concept, right? That's what you mean by communicator? Yeah, okay. That's the second part of the talk. So thank you for setting it up. It's, I think, the next slide. So before we get there, I think the answer for now is that, yes, the communicator is available to us. And the communicator, however, doesn't need to know. The point I was making just now is if you think in terms of CCLs and communicators, the communicator is basically saying, here's where my buffers live, transfer it over there. It doesn't need to know whether it's on the PCI local path this way, or it's across a network to another one of our devices on the other side, because the way you describe the source and the destination buffers is consistent and remains the same. There's no change. Okay? So what this allows you to do is, sorry, there's one more use case. So we talked about this use case, right, which is basically how we would do all-to-all within and without, right? So within this mesh, we could do an all-to-all. And again, the same scheme can be used to set up the all-to-alls going the other way. There's another use case that is actually even more interesting potentially. We don't talk about it too much because it does require some other component or somebody else to do some work for us, but that is a reduced scatter accelerator. So a thing you can do with a scheme like this is you can effectively say, I have hardware accelerated reduced scatter. So Dr. Panda was talking about compression, right? One of the problems, if you're trying to do compression or you're trying to do reduction is, whatever you do, let's say a scheme you want to consider is you had an accelerator that could do compression or acceleration, and it was attached to one of our PCI ports. A problem you have to worry about is a 4-to-1 overspeed on that port in this example. Because no matter what you do, these guys are going to produce 4 times the bandwidth that whatever device you connect here is able to consume. You could make it a 4x larger device and consume even more bandwidth, but then you're losing connectivity for the nominal case, right? Like if one of your accelerators take 4 ports, then when you're not using that accelerator, you've lost 1/4 of your ports and you didn't need to. So one of the things we can do is effectively implement reduced scatter inside the device, which means you connect your devices and every device will see only 1/4 of the net bandwidth that you need. So now you can use a lower power compressor, you can use a lower power reducing engine, just connect more of those devices, and we will be able to shape the traffic such that each of those devices will be exposed only to 1/4 of the bandwidth. So you don't have to build some ridiculous device to try to support this function. While you can do both of those things, in a scheme like this, if you can multi-home it and you can build that fat tree that we were talking about earlier, what this allows you to do is to allow ACF instances at 3.2 terabits each. Every one you add adds to the bandwidth. This, for example, is a solution to the memory wall problem, right? You can stack memory here. You can stack memory across an RDMA surface into a box like that. And the bandwidth that you need is supported and solved by simply stacking up more of these devices. And what you're doing is you're paying bandwidth for latency, which is a true problem. But if you have a structured algorithm where latency can be actually managed by increasing batch size, compute block size, or matrix size, then you can make that trade-off in a very systematic way, such that you get the bandwidth that you need without having to compromise your overall throughput. Okay. So that's section one. The second section I want to talk about, which was preset already for me, is the network side of the house, right? So far we talked about the compute side of the house. Now we're going to talk about the network side of the house. So the other thing that we did that was different, right? So every RDMA NIC in existence that we know of has come up with the model that I'm going to go build my entire transport and bake it into ASIC, into silicon. It'll be very hard to touch. And the conventional wisdom has been, you have to do it that way because any kind of solution that does not have hardware very close to the wire is unmanageable and unsustainable. We wanted to challenge that because that has led to two problems, right? And it leads to the model that we heard yesterday also of, oh, but we have now a very nice DPU programming environment. You just have to learn to live with a very restricted memory address space, or you have to learn to live with limited instruction set, or you have to learn to live with limited signaling, which over time ends up becoming the tail that wags the dog, right? Networking systems and network architectures evolve not because that's the thing that you want, but because you're trying to overcome some limitation in the way the system is implemented. So in our system, what we did is we said we are not going to do that. What we are going to do instead is we are going to build, because the device is an aggregated super NIC, we're going to actually extrude the control plane out of the chip. So the way the control plane works is with a companion processor that's plugged into one of our ports, and the hardware is capable of sending all the control signals to this extruded processor. What that allows you to do, in very simple words, is that while hardware manages everything that is per packet, so pacing, steering, congestion reaction, congestion control, rate management is all done in hardware. Address translation is done in hardware. We have a very, very efficient receive and send coalescer in hardware, and flow control is in hardware. But software actually runs the transport. So you want to have a scheme, I call it a low frequency scheme, that sets what header rate you want to send, what ports you want to send traffic towards, what per collective operation you want to execute. That can all be done in software. And it runs in an open CPU. It's a CPU of your choice. There is no imposition on it. There isn't like, oh, but we selected this CPU and it has only this much address available, and this is the maximum buffer you can have, and so on and so forth. So this allows us to effectively split the path in an interesting way, such that you can run all your complex algorithms, all your traffic shaping on this thing. But more importantly, to answer your question very directly, the nominal design is that the access to this control plane, this control processor, which is through a hardware accelerated cache line size transfer unit that moves data at hundreds of nanoseconds per transaction, looks like a RDMA Wookiee queue, right? A word queue. But we have an implementation where that can actually be directly plugged into a CCL. So instead of telling the device, which a hardware implementation would have to have, that here's a send or a receive or a read or a write, and let me segment it for you and do all these things, you could actually come and say, do an all reduce. And the implementation on that core is going to be is going to be optimized for all reduce. It understands all of the input channels and net bandwidth that it can draw from, and it understands all the egress ports that are available to it. And in fact, it even understands the loading on those egress ports. So you do not have to then go and say, go break down this higher level collective operation into some low level function. This guy has the intelligence, or this component has the intelligence to say, this is the optimal path for this particular function and future functions that are queued up behind it. So let's look at that also in a little bit more detail, right? So, and I used our picture. I should have actually, I'll get to, let me explain the picture. I'll get to you in a second minute. I used our block diagram because it helps the build out. But you should think of this picture as a conventional picture of a stovepipe, where basically what you're saying is there's an accelerator or a processor here that's talking to a NIC, that's talking to a port, that's going through a cloud and getting to the other end. This is what a conventional device would look like. Yes, Manoj.
And I just previously said you can just talk about collectives to the NIC. That means you're expecting some interface that talks about, okay, it is my graph or whatever it may be.
So the interface, the hardware interface, we call it FabX internally, is think of it as a cache line sized queue. You write a cache line, we move it into this thing. And what's running over here is effectively a multi-core high IPC processor that is spinning on a whole bunch of address spaces. Right? So you can implement whatever you want on that messaging transport. And if today, like I said, the way we do it is we do, in conventional ways, take the CCL, shape it into a RDMA call through a provider library and move it to the other side. But we have an implementation where we are just short-circuiting that complete path. Okay, so the logical flow here, right? So like I said, this is what a conventional flow would look like. But here's a big difference. If you think about a conventional flow, this is a NIC. This is a switch, right? What that means is that the NIC is going to guess the state of the switch, and the switch is going to try to figure out what the NIC is doing based on a stream of packets. And it's almost, not almost, it's always in arrears. You're trying to figure out the state of the NIC by looking at packets that you've seen in the past and predict the future. In our design, because these two crossbars are within our device, the state of this, actually, if you think of this virtual queue is a complete representation of the state on both sides of the chip. Right? By looking at the way in which this virtual queue is progressing, I can tell you if the source has provided more data, and I can tell you whether the network is draining or not. And it is not a guess. It is 1000% deterministic, because I'm looking at my own counters to figure out if it's moving. Right? QoS at this layer is not required. Half of the scientific research in that area just goes out the window because we don't need it, because it is precise and deterministic. Once I have that, I can now queue up traffic such that I can correctly and appropriately load all of my network paths. Similarly, once I can get out on all of my network paths, like we talked about before, I can aggregate it back as well. What this allows me to do is effectively say that the sustained throughput path between my blue port on the left and the blue port on the right is always going to be deterministic. In between, you will need all of the variety of packet spraying and DLB type schemes that exist. You will need that, obviously, because all this device can do is at most make sure that the load is correct on this interface. But again, unlike a conventional design, which at the best will come up with a predictive scheme, put a token in here and hope that the cloud does the right distribution, what we are doing is ensuring that at start and at end, we will allow the full width. Now remember, we have 32 ports here, and we can go multiple devices in parallel. So this can be 256 ports of space immediately coming out of the accelerator, which according to the numbers we've seen is more than sufficient for all the use cases we were targeting. On this side, since this layer is really a router, the way that that layer works is one of two ways. It can act like a true router, so it's looking at Ethernet and forwarding, or it can act like a software router, in which case your CCL is giving us hints on what that routing policy needs to be. The CCL can tell us these, like it can say, put all gathers on a channel and put all reducers on a different channel, because many applications, and I'm looking at Manoj because they have put out papers on this in the public domain. If you're trying to run like a all reduce and a pipeline parallel, point to point in parallel, then what you need to do is actually structure these CCL such that they don't compete with each other. Otherwise, you're left with statistical competition, which is not needed. Like you knew everything that you needed to know, but then you told the network, hey, guess what I'm doing? Why? We can be much more prescriptive and deterministic about that. In addition, one of the things that we have, our, like, let's call it special sauce, is we have an internal circuit that allows us to, like as shown here, it allows us to effectively convey the state of this virtual queue to that virtual queue, effectively building a very long reach, InfiniBand-like credit control mechanism that's going across Ethernet. So the structural problem that Ethernet has, which is short bursts that you can end up with overwhelming switch ports, are effectively taken off the table, because what will happen, and there's a lot of detail here that I'm not going to get into, we have very sophisticated signaling here that gives us not just depth, but also rate and distribution, such that we can make sure that this guy effectively gets dequeued at the right time, because we know that the receiver queue is going to be falling behind. Okay. I expected some questions on that, but if not, we shall move along. And remember, in all cases, the data path is always parallel, right? So in all of these scenarios, okay, thank you, Manoj.
No, it looks like Pankaj is raising his hand a couple of times.
Oh, I see. Sorry, there's a question on the phone. Can I hear them if they ask?
Am I unmuted?
I can hear you, Pankaj. That's Pankaj?
Okay. Yeah, hi, Srijeet.
Yeah, hi, Pankaj.
So a couple of interesting points you have made so far. Let me ask them quickly one by one. Okay. One is you talked about a bandwidth for latency play. So, you know, in this kind of architecture that you're describing, one suspects that there might be pipeline bubbles due to you know, this flexible rate matching. So what does it actually take to prevent communication from getting exposed, you know, in the sense that architects at the upper layer talk about?
Yeah, okay. So were you going to list all of them, or did you want
No,
to
let me ask one by one.
Okay. The simple answer is software and people like you. Because the thing is, right, the hardware doesn't have an implicit bubble, and we will do work conserving scheduling. The point you're making, which is obviously true, is that if the work being doled out has bubbles, right? So let's say you are doing a conventional design where you have an application stack that's doling out work, and that application stack has to go service something before it gives you more work, which means your effective bandwidth is reduced because software was busy doing something else, as opposed to a pure hardware pull mechanism. There's nothing the chip can do or nothing we can do at our level, so we would have to figure out how to make that better. And one of the strategies we are looking at is implementing a CCL, but it turns out when you're a small startup, trying to build your CCL and getting everybody else to adopt it is not that easy. And I think I'm understating that heavily. Now, people here might be able to do better, but that's why we are here.
Very quick second question, Srijeet, if I can.
Yeah.
So this one is about, you know, your data movers and the possibility of global virtual addressing. So, you know, many things you try to do, especially the kind of collectives, fused collectives that some people are trying to engineer in PyTorch on top of symmetric memory and PGAS, require flexible virtual addressing. You said you have address translation in hardware, but you have a lot of software control plane. Could the hardware address translation be accessed from the software control plane?
Yeah, it can. Actually, you're right. Sorry, I just realized there's a slide I meant to put in, but I forgot. So remember, okay, so I'm going to quickly address this, and then how are we doing on time? Okay, I have 2 more slides, so we may be good. And then I'll rush through the data slide. So if you remember this part, Pankaj, remember these things are, I call them, I said they look like SGEs. They really do. So they belong to a PD, like in an RDMA context, and the PD defines your address translation. Now, the thing that we've done that's a little interesting is you can pass virtual handles to that PD to each other. So the way you build a multi-address space scheme is you define the address space and the translation in your local domain, and then you pass a handle to it to somebody else to use as an abstract handle. So by using these 2 contexts or these 2 concepts, software has complete control over which version of which address translation scheme it's using, and thus access the final address. And I realize that's a lot of words, and that might not be as clear as it needs to be. Maybe you and I can follow up on this offline later, or anybody else who has questions. But
sounds good.
Yes.
This is really good. Yeah, thanks a lot, Srijeet.
Yeah. Okay, so let's we are almost out of time, so let's just keep rolling forward. We talked about this part. Another thing that this really helps with, and Dan was talking about this earlier, about varieties of networking and varieties of network levels of performance. And actually, in fact, Dr. Panda talked about it as well. So this picture is a bit cartoonish, but it, I think, proves the point. The picture on the bottom is showing you what you could do if you had a 51 terabit switch and you were trying to connect 800 gig accelerators to it. To get full bisectional bandwidth, you would put 32 ports down and 32 ports up, because 64 ports of 800 gig is a 51 tera switch. With a device like ours, because we've effectively collapsed the first level of TOR, you could put 1,000 accelerators in the same tier, which means now you have 1,000 accelerators that are reachable in the same latency profile of a directly connected single 51 terabit switch. I think for this audience, I don't have to explain why that's a pretty dramatic shift in throughput, performance, latency, and the like. Now remember, you can, in addition to this, you can do all of the things I talked about earlier. So you can get all of your collective reduction, all-to-all acceleration, and all of those things, but now it's applicable at units of 1,000 accelerators. And in addition, just the fact that we have this huge path diversity, you get a huge performance, real-world performance boost. And what I was actually hoping to hear, but I didn't hear till now, is the problem that all of these ever larger clusters is running into, which is optical failing, right? Optical burnouts or problems with just connectivity. In the ML world, there's a term that gets thrown around a lot, MFU, which is not actually a bad word. It is a bad word, because the mean flop utilization is a thing, right? And because when you're building clusters at this scale, failure is going to become not a thing that sometimes happens, it will always happen. You have to deal with it. So one of the things we've seen is that having a 32 path diversity design along these lines gives you an option to effectively dramatically reduce the downtime you would see when your cluster size starts approaching these 50,000 and above sizes. So that was the networking side of the house. And just to show you a little bit of what we've seen in terms of measured performance, the thing I should state and remind people is that our chip has only been back and fully operational for a couple of months. So it's early days and we are going through a bunch of things. But one of the things that we saw, right, is if you look at this picture, one of the things it should be telling you is that standard ECMP networks perform much, much worse than multi-rail designs. But one of the things we bring to the table is use a platform like ours, do what we call message spraying. So rather than doing very fine-grained packet spraying, which has to come with a fairly sophisticated congestion control mechanism, but packet spraying, which is well understood, Meta has actually demonstrated